Kia ora koutou, no mai, haere mai. Welcome to lesson 25 for introductory physics. This is the first lesson in which we're going to start looking at nuclear physics, so the physics of atoms but within the atom. In the previous sections we've talked about atoms and we've talked about building solids and substances out of atoms. Now we're going to go the other way and have a look at what makes up atoms. As usual, we'll jump over and have a look through our lecture notes. So our goals are to describe the structure of an atom, state where atoms are made, state the difference between atoms of different elements, look at the number of protons, neutrons, and electrons in atoms, and then we're going to define a few terms, some of which we've already actually been using, but we're just going to give those definitions to be very clear about them. And then we're going to finish by talking about some types of exotic matter. So exotic matter being certain types of matter that you wouldn't deal with in your daily life. There is also the significance of the equation E equals mc squared, which is somewhere in the middle of this lesson, but I've put that as the last learning outcome because that is obviously a well-known equation, something to hopefully look forward to actually understanding that equation in a basic sense. So to start with the structure of an atom. What is an atom? Recall that everything is made up of atoms. They are very small, they are very numerous. A single hydrogen atom has a mass of only 1.67 times 10 to the negative 27 kilograms. So these are tiny, tiny things, but they make up everything we know, everything we are, and everything we interact with, all made of atoms. We can't actually view atoms. They are too small, so we can't look at them in the same way we look at other systems that we are studying. There are some special tools that allow us to create images of atoms, even at an atomic level. There are some tools that will create these pictures, but really it just shows them as being little lumps of atoms. There's absolutely no way for us to see what is inside an atom and what an atom looks like from any kind of visual sense. Instead, what we do is we come up with models of what we believe atoms look like, and we base this on experimental evidence. Now, what I'm about to say is not actually part of this course, but some people find it interesting. The way that we figure out what an atom is made of, what is inside an atom, is by smashing them together in things like Large Hadron Colliders, like you will have heard of Large Hadron Colliders, hopefully, like over at CERN. They speed these particles up, the atoms, and even smaller particles, and they smash them together and they look at the debris that comes out of it. And by looking at that debris, they try and guess, they work backwards and try and say, well, the atom must have been made of these different components. The same way that if you look at a basketball, there's absolutely no way for you to know what is inside that basketball. If you didn't create it, all you can see is the outside. But if you smash it into something hard enough that the basketball can break open, then you can start to make guesses about what was inside the basketball, and it's only air. For atoms, it's not that simple, right? There's obviously a lot more stuff in them than just air. Atoms make up air, so that wouldn't make any sense. So what we do is we come up with these models of what we believe atoms look like on the inside based on this experimental evidence, the data that we get from smashing them together at high speeds. So now pay attention again if you sort of zoned out there. We are back to content that I expect you to know. So what are atoms made of? They are made of a nucleus that on this diagram, it's a blue circle in the middle, surrounded by orbiting electrons, which travel around the nucleus. You can think of it like you think of planets orbiting the sun. It's not really the same thing, but it's a useful visual analogy. We're all familiar with the idea of planets orbiting the sun, so it's a good starting point for the idea of electrons orbiting a nucleus. The difference is that electrons can actually travel anywhere in a sort of a shell, a 3D spherical orbit, rather than just being stuck on one path like we have with planets, but it's the same sort of concept. The nucleus itself is made up of parts called nucleons. The nucleons come in two different types. We have protons, which have a positive electric charge, and neutrons, which have no electric charge. They are neutral. We are going to look at electric charge in the next section. Aside from their electric charges, so protons being positive, neutrons being neutral, aside from that, protons and neutrons are very, very similar. Their masses are almost the same. the difference in mass only becomes apparent if you start looking at 4 significant figures or more. So if you're only dealing with 2 or 3 significant figures, you can treat the masses of protons and neutrons as exactly the same. And they both occur in the nucleus with similar masses. The electrons that orbit the nucleus, though, they are very different. They orbit at different levels. We call them electron levels. You can think of that like you think of the different orbits of the planets. So we have Mercury being very close to the sun, and then move out further, and you get to Earth, and a bit further you get to Jupiter, and so on, all the way out to the pseudo-planet Pluto. So each planet is slightly further out, which means they're never going to hit each other. And it's the same with the electrons. The electrons all orbit on these different levels. So these different shells. So there'll be a shell close to the nucleus, and there'll be up to a couple of electrons on that, and then there'll be another separate level a bit further out, which can have some more electrons, and then another one a bit further out. So each of these shells, the electrons that are on that shell are pretty much stuck there. They can move, as we'll talk about in a separate lesson, but essentially while it's just on that shell, it's not going to come anywhere near the other electrons. All of those electrons have a negative electric charge. So protons are positive, electrons are negative, and the neutrons are neutral. Electrons are very small compared to the nucleons. The nucleons, the protons and the neutrons, remember we said were 1.67 times 10 to the negative 27 kilograms. The electrons have a mass of 9.1 times 10 to the negative 31 kilograms. Negative 31 versus negative 27. So the electrons are even smaller. The electrons are about 0.05% of the mass of the nucleons. And a nucleus can be made of many nucleons, so the nucleus itself can be very big compared to the electrons. We're going to talk about electric charge in the next section, as I mentioned. We're not going to go into great detail of it right now. We will then. For now, all I want you to be aware of is that positive electric charges repel other positive charges. Negative electric charges repel other negative charges. So positive repels positive, negative repels negative, but positive and negative charges will attract each other. Right? So if they're different charges, they'll attract. If they're the same charges, they'll repel. And the other key thing to know about atoms and looking at atomic structure is that protons and electrons have exactly equal and opposite charges. Exactly equal and opposite. So what are protons and neutrons made of? They're not actually as small as we get. Protons and neutrons themselves are made up of even smaller components called quarks and gluons, but we're not going to go there. We're not going to go any further into that realm of physics. Feel free to look it up if that interests you. It does get complicated, but you can certainly look some of that up. Protons in the nucleus, that makes the nucleus positive. Neutrons are neutral, so it doesn't matter if they're there or not. And if we're just talking about electric charge, it doesn't matter about the neutrons. All that matters is the protons are positive. The electrons, being negative, will be attracted to that positive nucleus. And remember, way back in mechanics, we talked about the idea of a centripetal force, a center-directed force, which caused an object to travel in a circle. The protons in the nucleus are attracting the electron, therefore the electron is experiencing a centripetal force and it will travel in a circle, and that is why electrons orbit the nucleus. They orbit because they're traveling horizontally around the nucleus. They have this perpendicular component to their velocity, but the attraction to the nucleus causes that to accelerate into a circle, and so we get this orbit path coming out. So that's the basic idea of the structure of an atom. We have a nucleus with protons and neutrons, and we have electrons orbiting it. The electrons orbit it because they are attracted to the nucleus, electrons being positive and the protons in the nucleus being, electrons being negative, protons in the nucleus being positive. An atom can, of course, have any number of protons in its nucleus, but different number of protons will have different total electric charges. And as we'll see in the next section, different amounts of electric charge means that things behave differently in terms of how they interact with other atoms and elements and substances in the world. So any atom which has a different number of protons will behave differently to all the other atoms with their own numbers of protons. And that's the difference between different elements. Different elements have different number of protons and therefore different total electric charges on their nuclei, which is the plural of nucleus, on their nuclei. We call that number of protons the atomic number. Right? It's the atomic number because it defines the atom. It tells us what type of element the atom is. So that's the most important number in terms of understanding how that atom will behave chemically, how it will interact with other atoms, other different types of elements or atoms. So hydrogen has a single proton, helium has is the second element, it's got 2 protons, lithium is the third, it's got 3, and we can continue onwards. Beryllium has 4, boron has 5, carbon has 6, etc. So the atomic number is the single property which defines which element that atom is. How many electrons, how many neutrons, as we're going to see, doesn't actually matter in terms of saying which element it is. All that matters is how many protons there are. If you know how many protons are in the atom, then you know which element it is with certainty. It's definite. Just a little bit of linguistics. The term atom refers to a single specific atom. If you say, I've got a hydrogen atom, you're talking about one specific atom which happens to be hydrogen. If you talk about element, then you are talking about a type of atom, but it can be any atom of that type. Right? So if you just say the element hydrogen, you could be talking about any hydrogen atom or all of them. Whereas if you just talk about a hydrogen atom, you're talking about a single specific one. It might be a real one or it might be a hypothetical one, but you're talking about that specific one. Since the number of protons is all that we need to know in order to tell us which element an atom is, that's the obvious way to organize the elements, is basically a list going up in terms of the proton number or the atomic number. As we said, hydrogen has 1, helium has 2, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, etc., etc. And they're all just listed in order of proton number. And as you can see, it forms a nice little table like that. We're not going to worry about the distinction between different rows and columns and things in this course. That's getting into chemistry. If you do chemistry, you'll already be familiar with the periodic table and you'll understand different parts of the table. If you don't do chemistry, then you don't need to know it for this course. I'm just mentioning it because you will be aware of the periodic table, and that is the reason for it. It lists the elements by atomic number. We said that protons are all positive, we said they're all in the nucleus, and we said that positive things repel other positive things. So shouldn't all the protons repel each other? Yes, they should, and they do repel each other, but there is an even stronger force called the strong force, imaginatively, that holds all of the neutrons and protons together inside a nucleus. We'll talk more about that in the next lesson. So for now, you can not ignore the fact that protons are positive and repelling each other, but just recall that there is going to be something else that still holds them together, that glues them together to hold all the protons in the nucleus, even though they're all positive and are repelling each other. Right, so those nucleons, all of them, that's all the protons and all the neutrons. I can't remember if I actually defined that term on any of the slides, but nucleons means protons and neutrons. Anything you find in the nucleus is a nucleon. So all the protons and neutrons will hold each other together using this strong force, even though the protons are trying to push apart. Since the number of protons determines the element, can we change the number of protons to make a different element? Yes, we can, sort of. I say we can, but we can't really. It's pretty difficult. The forces involved are very, very large, so it is very difficult for us to change atoms of one type into another. If you take 2 hydrogen atoms which have a proton and a neutron in the nucleus and push them together with lots of force, then you can merge them into a helium nucleus, 2 protons and 2 neutrons. So you certainly can do that. It's just very, very difficult. It requires a lot of force, a lot of pressure, a lot of temperature usually. So then where do atoms come from? If we can force them together, but it's very difficult, how is this happening naturally? In stars. Stars are very huge, they're very hot. The atoms inside of them are subjected to huge forces, huge temperatures, and these forces are strong enough to force those nuclei together. They will force 2 hydrogen nuclei together and form a helium nuclei, and they will force a hydrogen and a helium together and form a lithium, and so on. They will force atoms together, merge the nuclei together, and form larger atoms. So all atoms are made in stars. Apart from hydrogen, hydrogen was the initial one that's just there in the universe abundantly. These heavier atoms are created inside the cores of these huge stars, and when the star dies and explodes, it sends these heavier elements out into the universe. If that had never happened, if no stars had ever died, then we would not exist. Anything bigger than hydrogen in the universe would not exist. Everything that we are made of, carbon, oxygen, nitrogen, all of those, they're all made in stars, and the only way they get released from the stars is when the stars die and explode. Because heavier elements need this kind of extreme force and pressure, these extreme conditions, in order to be formed, it means that most elements, most atoms in the universe, most matter in the universe is actually just hydrogen. About 74% of all the mass in the universe is hydrogen. And helium, which is the easiest one to form, right, just take two hydrogens and smush them together. It's still hard to form for us, but it's easiest to form in terms of the scale of forming different elements. Helium is the easiest to form, so it accounts for about 24% of all matter. And that means that we only have 2% of all mass in the universe left to account for everything else. Everything on the periodic table that is above helium only makes up 2% of all mass in the universe. So it's a tiny, tiny portion of all of that mass. That means that you, me, all other human life, all other life in general, all other planets are all made of all these other types of atoms. We are all made of stuff created in long expired stars. Stars created them in their cores, the stars died and exploded, sent them out into the universe, and millennia later we form. Right? We form out of these dead remnants of stars. Atomic masses, there's not just atomic masses in this part, but I just sort of lumped everything together into atomic masses. So we're going to jump around a little bit in this section and look at a few different things. So we've talked about protons defining the element which an atom is. We've talked about neutrons being part of a glue that holds these protons together, but they are electrically neutral. So they don't change the properties of the atom in terms of what it will do chemically when it encounters other atoms. So what does the number of neutrons do? Nothing, really. Right? It doesn't change the element at all. That means that you can have an element or an atom of an element that exists with different numbers of neutrons. And these different numbers of neutrons, these atoms of the same element with different numbers of neutrons, they are called isotopes. So you can get hydrogen on its own with just a proton. Right, so the nucleus of a hydrogen atom could be just a proton, no neutrons at all. Because there's only one proton, it can't repel itself, so it doesn't actually need any neutrons to sort of glue it together with that strong force. So that's perfectly acceptable to just have a single proton as your nucleus of a hydrogen. But you can have a neutron there. There's nothing to stop you having a neutron. It doesn't change it. It's still hydrogen because it's still only got one proton, so the electric charge of that nucleus is still the same. So you can add a neutron. You could add two neutrons. You could add three. You could add many more neutrons if you wanted. As we'll see in the next lesson, though, that's not always going to be stable, something we'll talk about next lesson. But you can have one or two neutrons quite happily on a hydrogen nucleus. And so these are different isotopes of hydrogen. We have hydrogen with one proton, hydrogen with one proton and one neutron, hydrogen with one proton and two neutrons. So we have different numbers of nucleons in each of those nuclei. As I just said, hydrogen doesn't need neutrons, but it can have some. Copper has 29 protons, 29 positively charged protons in its nucleus. They are all going to be trying to repel each other. So copper needs some neutrons. The strong force just between the protons isn't enough to overcome the repulsion between those 29 protons. So copper needs some, but it doesn't need a specific number. It can have any number of neutrons as long as it's got enough to glue them together and not too much that it becomes radioactive, as we're going to talk about in the next lesson. And so what happens is that anywhere around 34 to 36 neutrons is ideal for copper. 34 and 36 are the most common ones. In fact, they're the ones that we find naturally occurring, is just 34 and 36. But it can exist. It can exist with anywhere from 23 up to 51 neutrons. So the exact number of neutrons isn't specified, right? It's not determined by the element itself. The exact number of neutrons can vary based on whatever just happens to have formed that copper atom. Since the mass of protons and neutrons is about the same, the total mass of the nucleus will depend on the total number of nucleons. So the atomic number, the number that determines what element the atom is, just depended on the protons, but the number of nucleons, so protons and neutrons all together, that determines how heavy or what the mass of that nucleus is. And so that total number of nucleons, that's what we call the mass number. For that reason, it determines what the mass of the atomic nucleus is. A hydrogen atom with no neutrons would have atomic number and mass number both being 1. It's just got a single proton. So the atomic number is 1 because it's got 1 proton, and the total number of protons and neutrons is still only 1, so it has a mass number of 1. Copper, as we saw, has 29 protons, so it has an atomic number of 29. But a copper atom with 34 neutrons has a total of 34 plus 29, which is 63 nucleons. So it has a mass number of 63, an atomic number of 29, but a mass number of 63. So the mass number is the number of protons and neutrons all together because they all have pretty much the same mass. Because the atom has a unique atomic number, but the mass number can change, it is common to write down the different isotopes of an element. Right? Write them down as you're talking about them. We commonly do it as element name and then mass number, follow that. So a dash, then the mass number. So you might get hydrogen-1, meaning hydrogen, just a single proton. You might get hydrogen-2, which is hydrogen with 2 nucleons. We know hydrogen only has 1 proton, so therefore it must have 1 neutron. Same thing, hydrogen-3, we know it must have 2 neutrons because it has 1 proton because it is a hydrogen. Copper-63 and copper-65 being the ones we talked about before. Copper, if you know the atomic number of copper, then you can tell how many neutrons are in there based on that mass number. This is sometimes also written using the atomic symbol and a superscript mass number, which is 1H, 2H, those are hydrogen 1 and hydrogen 2. Copper-63 would be 63, and then Cu for copper. I don't expect you to know the atomic symbols. If you do chemistry and you do know some of them, that's fine, but I don't expect you to know them. I will provide any atomic symbols that you will need when you need them. All right, so we've talked about the nucleus a bit. What about the electrons? How many electrons are there going to be on an atom? The electrons are orbiting the nucleus. Remember, they're flying around outside, held in by that centripetal force of the attraction between the protons in the nucleus and the electrons being negative. So they're held in by that, but they're orbiting. And because they're orbiting, there's none of this strong force that holds the nucleus together. It's actually relatively easy to add or remove electrons to your atom. The closer you get in to the nucleus, the harder it can get. So a hydrogen, you have a single electron and a single proton. That force isn't too big, so that you can add or remove that atom, that electron, I should say, from that atom. That's not too hard. If you take copper, copper has 29 protons. If it starts with 29 electrons and you start pulling them away, by the time you get down to the last few, you've got electrons that are in the lowest shell, really close to this really positive nucleus because it's got 29 protons. So you've got 29 times the attraction that you would have on a single electron on a hydrogen atom. So it gets really hard by the time you get into those closest electrons, but that doesn't happen. We only ever deal with the outer few electrons. And so the outer few electrons aren't that hard to add or remove. So the sum of everything I was just saying on this slide is that electrons can relatively easily be added or removed. If an atom is electrically neutral, then that means that it must have the same number of protons and electrons. Remember that protons and electrons have exactly equal and opposite electric charges. So that means if you take 1 proton and 1 electron, you have a net electric charge, a total charge of 0. Right? That's like adding $1 and taking away $1. You end up with 0. Proton, you add a bit of positive charge. Electron, you add a bit of negative charge, which takes away that charge. You end up with 0. So a neutral hydrogen atom with 1 proton must have 1 electron. A neutral helium atom with 2 protons must have 2 electrons, and so on. So a neutral atom will always have exactly the same number of electrons as it has protons. If the number of electrons is different, If you've got more or fewer electrons than the number of protons, then the atom will have an overall electric charge. If you've got a hydrogen atom and it's got an electron and a proton and you add a second electron, all of a sudden it's got a total negative charge because it's got more negative particles than it does positive. So it ends up with a negative charge. If you take the one electron off a hydrogen atom and you're left with just a single proton, then you've got a net positive charge. So whenever you have a net charge, because you've added or removed some electrons, you call the atom an ion. So a positive ion has lost electrons, a negative ion has gained electrons. It's important to remember that we only ever add or remove electrons to form ions. We only ever add or remove electrons because if we change the number of protons, if we removed a proton so that the atom now had a net negative charge, it's a different element. Right? We've got a different element. We've actually changed the element entirely. So that's not what we do. We can't physically just reach in and take out a proton, but we can cause chemical reactions where an electron will be removed. So far, we've talked about scientific notation in this course quite a bit. We've talked about masses of protons and neutrons and electrons already in scientific notation as being, negative 27 kilograms, right, in that region. But sometimes when we're doing a lot of work, even scientific notation becomes cumbersome. Having to write out times 10 to the negative 27 every time you write a mass will get very boring, very tedious, and quite messy, to be honest. So what the physicists did is came up, or it may not have been physicists, it may have been any scientists, came up with the atomic mass unit, or AMU. 1 AMU is equal to 1.660540 times 10 to the negative 27 kilograms. And that is the mass of a single nucleon, approximately the mass of a single nucleon. And it allows us to write atomic masses in much simpler forms, as we will see here. A hydrogen 1 atom has a mass of 1.008 AMU, which to get the mass in kilograms, we just multiply by 1 AMU, which is 1.66 times 10 to the negative 27. So we get 1.67 times 10 to the negative 27 kilograms for a hydrogen 1 atom, which is just the mass of a proton and should be no surprise. Carbon 12 atom has a mass of exactly 12.000 AMU. It's exactly 12. That is how the AMU was actually defined. It's 1/12 of the mass of a carbon 12 atom. And if you multiply that by 1 AMU, you get out 1.99 times 10 to the negative 26 kilograms. And similarly for aluminium 27, a mass of 26.982 AMU, which gives us that mass in kilograms. So you'll notice that they're all slightly off. Right? The carbon 12 is exactly 12 AMU, but hydrogen is slightly above 1 AMU, and aluminium 27 is slightly below 27 AMU. So what's going on there? It turns out that adding nucleons together does not result in the mass being the same as the mass of all the separate nucleons added together. And that's something that we're used to in our everyday life. If you take 1 kilogram of something, you add another kilogram of something, you're going to get exactly 2 kilograms of something. That's what we're used to in everyday life. That doesn't work in atoms. When we're talking about creating nuclei from different protons and neutrons, that no longer works. And this is where we bring in the most famous equation. Pretty much everyone has heard of this. You see it on posters, you see it on socks, you see it on shirts, you see it everywhere. It's a very common equation. You see it in bad movies where they're trying to make it look like someone knows some science. But what this equation actually means is relatively straightforward. E equals mc squared. E is energy. We've already met that. This idea that we have energy is not new, hopefully. E is energy. M is mass. Again, we've met mass. We know mass. C is actually the speed of light squared. We haven't really met the speed of light yet, but it's just a speed, it's just a velocity. So what we have on the left is energy, and what we have on the right is mass times some speed. And what the equation is actually telling us is that energy and mass are related. They are fundamentally derived from the same thing. So what happens is that when you take two nucleons, a couple of protons or a proton and a neutron, and you push them together and you form a nucleus, some of their mass is used as energy. They use their mass as energy. That is what the equation is telling us. It's telling us that fundamentally, those two things can be used for the same process. They can be interchanged, exchanged, however you want to phrase it. They can be used. So when nucleons form bonds and form a nucleus, they use some of their mass as energy. That's a slightly oversimplified version of what's going on. It's certainly not enough for you to go off and do any calculations and figure out these new different masses, but it hopefully explains the core idea behind nucleons having different masses. So as we saw, if I just go back a couple of slides, as we saw hydrogen, one atom, it hasn't formed a nucleus yet. It's just a lone proton. So a lone proton has that mass of 1.008 AMU. So that's fine. But if you take 12 nucleons, so carbon being 6 means we've got 6 protons and 6 neutrons. So you would expect 6 times 1.008 AMUs. You would expect that. But instead we just get exactly 12. So we've lost some of that mass. If you take 12 protons and neutrons, which all have a mass of about 1.008 AMUs, and you add them all together, you would expect 12 plus 12 times the 008 part, but instead you just get 12. And so some of that mass has gone. Some of that mass has just seemingly vanished. But what the equation E equals mc squared is telling us is that mass hasn't vanished. It's been used as energy in forming those bonds between the protons and neutrons in the nucleus. So that is what the most famous equation tells us. For that reason, all of the elements with their different atomic numbers and different nucleus sizes have different mass per nucleon. Different mass for every proton and neutron. If you take a proton in a helium atom and you take a proton in an iron atom, they will have different masses, just slightly, but they will be different. And they are different because it has used a different amount of its mass to form the bonds that it created when it created the nucleus. And so this graph here, there's no numbers on it. There's no specific scales that I want you to learn or values I want you to memorize. The point of this graph shows us that hydrogen has the biggest mass per nucleon because it hasn't formed any bonds yet. As you move to the hydrogen 2 nucleus or hydrogen 3 nucleus, the mass per nucleon is getting smaller. As you move on to helium, it gets even smaller. More bonds forming means more mass being used as energy. And that continues all the way down until you get to iron. Right? Iron, I'm pronouncing the R specifically, even though it sounds weird because we've talked about ions as well being positive or negatively charged atoms. So iron, which I know sounds silly, but I'm going to say that just for clarity. When you get down to iron, then you get the lowest mass per nucleon. As you go above iron, up through heavier atoms all the way up to uranium and so on, as you go up, the mass per nucleon actually starts to get bigger again. It starts to get bigger again because the way the nucleus forms just doesn't need as much energy per nucleon to be used to form those bonds. We're not going to go into why exactly, just the fact that it happens. So iron has the lowest mass per nucleon. If you get into smaller atoms, you're getting less bonds forming and you get less mass being used as energy. If you get into bigger atoms, then the energy per nucleon needed is actually going to be less, and so you end up with a higher mass per nucleon that way as well. As I said, don't worry about me trying to figure out any numbers or formulas or anything off this. Just remembering the idea, the shape of this graph, and the idea of E equals mc squared. The purpose of it is to hopefully just understand that difference in mass per nucleon. And that's going to come back to us in the next lesson. We are going to return to this concept of different masses per nucleon. Actually, might be the lesson after that. All right, so are masses different for ions? Since electron mass is so small, not really. Losing an electron or two, not really going to be noticeable in terms of the total atomic mass, so no. Electric charge is different, but mass not really different. Mass is different for isotopes. Absolutely yes, that is why we have the mass number. Right? The mass number is defined as the total number of protons and neutrons. And that different mass number means a different isotope. And because a different isotope has a different mass number that's how it's defined, that means we're going to have different, different masses. So which mass do we use then? If different isotopes have different masses, how do we know which one to use if we're doing a calculation? For example, suppose you dig up some copper you refine it, and you end up with a lump of pure copper. So you've taken every other element out, you've got only copper, but you don't know what the isotope is. How do we know which isotopes there are and how much of each, and thus what the atomic masses are that we have? How do we know any of that? In nature, each atom, or each element I should say, each element occurs with a specific abundance. The abundance is basically the probability of finding that isotope instead of a different one. So the ratio of the different isotopes. Of copper on Earth, there are only actually 2 isotopes that occur naturally. Copper-63 and copper-65. The abundance of copper-63 is 69.15%, and the abundance of copper-65 is 30.85%. You'll notice, obviously, they total to 100%. So if you take any lump of naturally occurring copper, then you know that 69.15% of it is going to be copper-63 and 30.85% of it is going to be copper-65. Remember, atoms are really, really tiny. If you only took a couple of atoms, it's kind of hard to say which isotopes they would be. But a couple of atoms is not something we can ever really interact with, because we're talking about 10 to the negative 27 per proton or neutron, so really small atomic masses. So a couple of atoms, you can't really do anything with it. Anytime you get to a level of copper atoms that you can actually interact with and do any science with, we're talking about just so many of these copper atoms that this average is going to be about right. So it's going to stick. It might vary by a few atoms, but that's not actually going to affect the calculations that we're going to do. Since we have different isotopes with different masses, both occurring and both naturally obtained, then any element, any sample you take of an element will contain those different isotopes according to their different abundances. If you create the element in a lab somehow, if you were to create some copper, then you could force it to create either just copper-63 or copper-65 or even one of the other coppers that aren't naturally occurring. You could force it to do that, but if you just go and get some naturally occurring copper, then you know that the copper atoms are going to be in that ratio of their abundances. And so what the standard atomic mass is it's the weighted average of the masses of those different isotopes. So if your lump of copper has 69.15% of copper-63 and 30.85% of copper-65, then any lump of copper you get, you know, is going to have those ratios. Suppose you took 10,000 atoms. This is still a small number of atoms, but I've chosen that just so that I can work with the numbers on the screen. Suppose you took 10,000 copper atoms, then according to their abundances, you would get 69,015 copper-63 atoms and 30,085 copper-65 atoms. So the average mass per atom is going to be closer to the copper-63 than to the copper-65 because you've got more of the copper-63s. But to calculate that standard atomic mass, all you need to do is multiply the atomic mass of each isotope by its abundance. Now remember that the abundances are percentages, so when we're multiplying, we get rid of the percentage sign and we divide by 100. So instead of 69.15%, we multiply by 0.6915. So we take the atomic mass of copper-63 and we multiply that by 0.6915. We take the atomic mass of copper-65 and we multiply that by 0.3085 for 30.85%. That gives us a standard atomic mass of 63.546 AMU. There is an exercise for you to do that on the worksheet to go through and calculate the standard atomic mass, but that's all it is. Just multiply each atomic mass by its abundance and then add them up. That's all you have to do. And this isn't really to do with atomic mass, this is to do with atomic size, but I've left it in the part about atomic mass because it didn't really warrant its own section. So atoms are all different sizes depending on how many protons and electrons there are. Remember that the protons are positive, the electrons are negative. If you've got a bigger positive charge in the middle, then you're going to pull that electron in a bit closer and that electron shell is going to get a bit smaller. The nucleus is a tiny center to the atom. It's actually really small, as we're about to discuss. It's the electron orbitals that determine the actual size of the atom. So when you're talking about the size of the solar system, you don't talk about how big the sun is, you talk about how big the orbits of all the planets in the solar system are. It's the same thing with atoms. When you talk about the size of an atom, you don't talk about how big the nucleus is, you talk about how big the outer electron orbitals are, how big those biggest electron shells are. That is what determines the size of the atom. So with that in mind, you'll see that the atom sizes don't actually change that much. Even though the number of protons and neutrons in the middle, the nucleus, might be changing in size quite a bit, right? The copper is certainly going to have a much bigger nucleus than hydrogen. You'll see that the atom size overall is not changing that much, because it's the size of the outer electron orbitals that determines that atom radius. So for hydrogen, we have an atomic radii of 120 picometers, pico being 10 to the negative 12. So if you remember your prefixes, that's 10 to the negative 12. Helium, slightly bigger, 140, carbon, 170, copper back down to 140, cesium, 340. But these atomic radii are not fixed. Electrons are orbiting the nucleus. Electrons are negatively charged. Other forces can affect the size and shape of atoms. If they're exposed to other electric charges, then the electrons are going to be doing slightly different things. The atomic size is going to change. The atomic shape might change. You might get a sort of an oblong spheroid instead of an actual ball sphere. So these are just rough guides. They vary. Do not take them as being definite, exact, always true values. It's just a rough approximate value for us to get an idea of the size of these atoms. So if that's how big the atom is, how big is the nucleus? I said it's small. It's very, very small. Imagine that the atom is the size of an entire football stadium. Doesn't really matter which one, to be honest, just any football stadium. Just think of the last one you were in, or if you've ever driven past one, how big they are. Imagine the electrons are orbiting the outermost ring of the whole stadium, right behind the very outermost seats, or even right on the very edge of the wall of the stadium. Imagine the electrons are orbiting that. If that's how big the atom was, the nucleus would be the size of a pea sitting in the middle of the field. That's how tiny the nucleus is. So it doesn't really matter whether you've got a hydrogen, a copper, an iron, a cesium, whatever atom you've got. It doesn't really matter, because the nucleus is so small that relative to the size of the atom, that nucleus size isn't going to change it much. The bigger proton, the bigger the proton count, the bigger the atomic number, then the more it's going to pull some of those electrons in, and the more the closer the closest electrons will be, but the outermost electrons will still be about that same size. And that's what we saw. If I go back a slide, that's what we see, is that the radius of the atom only varies by, gets maybe twice as big, but it's not getting really, really big. So again, no specific values, no specific formula to memorize here. Just, I want you to get an idea of the scale of these atoms. These atoms are in the order of a couple of hundred picometer radius, and the nucleus within that is, if the electrons were the size of a football stadium, the nucleus is the size of a pea. We've already talked about building stuff out of atoms. We've said that everything is made of atoms. We talked about solids and liquids and gases, but we did skip a couple of steps, a couple of terms to define, so we're just going to do that now quickly. We talked about metals being a solid, and they form a crystalline structure. All the solids bond to all their neighbours. When they do so, they share their outermost electrons with all the other metal atoms in the solid. So a metal is essentially a crystalline solid with a sea of electrons that can move about between all the atoms. That's what a metal is. A molecule is the idea of a few atoms grouping together and bonding, not to make a whole solid, but just to make a little group of atoms. Those atoms might then, once they've formed a molecule, they might then make a solid or a liquid or a gas, but they'll still stay as that molecule. So that molecule occurs first, such as water, which is one oxygen and two hydrogen molecules. They will join, they will bond. The two hydrogens will share an electron each with the oxygen, and we get H2O, which is water. That water molecule can then form a solid. It can become ice, or it can form a liquid and become liquid water, or it can form a gas and become gaseous water in our atmosphere. That can take any state, but that molecule will still remain as a molecule. It will still stay as H2O. If two nitrogen atoms come together, we get the same thing. We get an N2 molecule. No, they will share 3 electrons each, so they've got 6 shared electrons. They will form a little N2 molecule, and again, that molecule can become different states. Solid nitrogen is very difficult to create, but you can certainly create liquid nitrogen that is very cold, and that you will have heard of that as a coolant for liquid nitrogen. We use it in the lab occasionally. Or more commonly, you get gaseous nitrogen molecules, which are a big part of our atmosphere. But regardless of the state, it is still going to stay as a nitrogen molecule. Of course, these molecules can be undone through chemical processes, but just through our temperature changes and our phase changes and all of that kind of stuff that we've talked about in this physics course, those molecules are going to stay as the molecule they are. If a substance is made of molecules which contain different types of atoms, then we call that substance a compound. So water, H2O, is a compound because water is made of molecules and each molecule has different types of elements in it. Fructose, a type of sugar which has C6H12O6, so 6 carbons, 12 hydrogens and 6 oxygens, that is also a compound because the solid sugar is made of molecules, right? Made of molecules which are all made of different types of atoms. Nitrogen N2 is not a compound because even though it's made of molecules, each molecule is made of the same type of atom, same element. So all compounds are made of molecules, but not all molecules make up compounds. If different molecules or atoms are brought together but do not bond in any way, they just occupy the same space, you've mixed them all up, then that's what we call it. We call it a mixture. The air we breathe is a mixture because it contains 78% nitrogen molecules, 21% oxygen molecules, 0.93% argon atoms, 0.04% carbon dioxide molecules, and even smaller amounts of neon, helium, methane, water vapor, etc. There's a whole bunch of different stuff. They're all in the air. But what you don't get when you mix air together, when air is formed, the nitrogen oxygen molecules don't go and interact with each other and form some new nitrogen oxide thing. We don't get that occurring. The nitrogen still stays as a nitrogen molecule. The oxygen still stays as an oxygen molecule. They just happen to be in the same area bumping into each other. And so that's called a mixture. After atoms have bonded, work or energy is required to pull them apart again. So breaking molecules. As I said, everything we tend to deal with in this course, we're not going to be looking at breaking molecules apart, but it does happen. It's a big part of our life. And obviously, if you deal with chemistry or biology, you will be working with breaking molecules apart. So that takes a lot of energy, as we saw, we haven't seen it. It takes a lot of energy to change these things, like plants taking energy from the sun, which we've talked about. We absorb radiation from the sun. Plants absorb that radiation, they put it to use. They pull apart the carbon and oxygen from a carbon dioxide molecule. They pull apart the water molecules and get hydrogen and oxygen, and they put them all together and they create carbohydrate molecules such as fructose, C6H12O6. So these molecules are effectively storing the energy the plant got from the sun. It's taken that energy and it's used it to create a molecule which has more bonds and therefore more energy stored inside it. And we can access that energy when we burn those molecules, either literally in a fire or metaphorically, we burn them using metabolic processes in our cells. So as I said, we're not going to go into that, just a little mention of it there for you out of interest, but we don't expect you to learn any of that for this course. The last part of this lesson is just a very brief tour through some exotic matter. And I say some, I'm really only talking about a couple of types. But exotic matter is the idea of matter that's not what you would encounter on your day-to-day life. And we've talked about the idea that everything on Earth, everything we're made of, everything the planet is made of, is all made out of matter, out of atoms, out of hydrogen, carbon, oxygen, nitrogen, and so on. Exotic matter is everything else. So everything that isn't made of all the types of elements and atoms that we've been talking about in this lesson. Anything else. So even something like plutonium, which is rare and it's radioactive, as we're going to talk about in the next lesson. Even something rare like that, that's still just normal matter. It's still just made of electrons, protons, and neutrons. They just do some odd things relative to other matter, but it's not exotic matter. Exotic matter is things that are not even made of protons, electrons, and neutrons. The first one is antimatter. we talked about positively charged protons and negatively charged electrons. Can we do the opposite? Can we create a negatively charged nucleus and have positive particles orbiting it? The answer is yes, but. Yes, but we cannot just put electrons in the nucleus and put protons in the orbital position, because the protons are really big, the electrons are really small, the physics doesn't work. That is not a possible format. However, there are opposites of protons and electrons. You can get something that is just like a proton but has a negative electric charge, and you can get something that is just like an electron and has a positive electric charge. These are known as antiparticles, and they are a type of exotic matter. So antiparticles are not your regular protons, electrons, and neutrons. You get an antiproton. Right? An antiproton has a similar mass to a proton, but it has a negative electric charge. An antielectron has a similar mass to an electron, but has a positive electric charge. The antielectrons are also known as positrons, and you can make an antielectron orbit an antiproton and create an anti-atom. Right? If it was just a single antielectron and a single antiproton, it would be an antihydrogen atom. But you can create them, and indeed one was created in a lab. In 1995, they managed to create an anti-atom. The problem is that anti-atoms, or antimatter in general, will annihilate normal matter. If an anti-atom and a normal atom collide, then they both essentially just disappear. They blink out from existence. They're gone. And that's what happened. They created one in a lab in 1995, but it annihilated very shortly after because it came into contact with real matter. It's impossible to stop it touching anything else in the universe, and so it did, and it annihilated. If a planet was made of antimatter and we built a ship out of our normal matter and sent it off to land on this antimatter planet, then the ship and the planet, as soon as they came into contact, would just disappear. They'd just annihilate, right? They'd just be gone, they'd blink away. If the atmosphere of this planet was made of, or if it had an atmosphere that was also made of antimatter, then as the ship, our ship made of normal matter, approached this atmosphere, it would just slowly fade out as it collided with the atmosphere, and all of those antimatter particles, all of its matter particles would just annihilate. It's believed that the observable universe contains only galaxies of matter. As I said, we know antimatter exists. We've created it in labs. We can work with it. It's very difficult, but it does exist. But the observable universe that we can see only appears to contain galaxies made of actual matter, our normal matter. But beyond that, there may be entire galaxies composed of antimatter. We don't know. There's no way for us to know. By definition, the observable universe is as far as we can see, so we can't see beyond that. So that's antimatter. Again, I don't expect you to memorize a whole lot of this. I want you to be aware of antimatter and the idea that antimatter and normal matter would annihilate, but that's sort of it. I don't expect you to go into any great detail about that. The other type of exotic matter we're going to talk about is dark matter. Dark matter is an interesting one. We know that stars are made of elements we have here on Earth because we can see the stars. We can see the stars, we can do some analysis on the light coming from them, which we'll mention later on in the course, and we can tell what elements the stars are actually made of. Even though we can't go over and collect some of the star and check it, we can tell just based on the visual information we get that the stars are made of the same elements that we have here on Earth, and we can even figure out which ones. There's no variation in the laws on how electrons, protons, and neutrons can assemble into different atoms. That doesn't change throughout our observable universe. We can see all these different stars, we can see these distant galaxies, we can tell that they are all made of the same stuff we're made of here, following the same physics laws. However, we can also measure gravity. We can measure the force on due to gravity between different stars and planets and things based on our measurements and our observations of them. And what we've found is that there are larger forces due to gravity than we would expect based on the matter that we can see. So the matter we can see would cause gravitational forces, but the ones that we observe, the forces that we observe, are greater than what we'd expect based on that matter. So astrophysicists have coined the term dark matter, and that means simply matter we can't see. It's dark. We can't see it for some reason. We don't know why. We don't even know what it is. But we know that there must be something there, because there must be something to cause that extra gravitational force. Right? We don't know what it is. It's clearly nothing that we're familiar with, so we're not set up to observe and detect it, but it must be something there. So that's a great big unknown for physics. It's one of the unknown things that is being investigated and hopefully be resolved at some point in the future. There is also some kind of energy which is serving to continually expand the universe. The universe is just constantly expanding. And again, we don't really know why. And the energy that is powering that expansion is referred to as dark energy. So basically, the term dark is just a code word for physicists saying we don't really know. Right? Dark matter, we don't know matter. Dark energy, we don't know energy. It is believed, based on scientific observations, that dark matter and dark energy make up around 90% of the universe. So most of the universe is stuff that we don't even know what it is. So very fascinating and also slightly concerning. And that's the end of this lesson. So as I said, it was a bit of a tour across a few different things, but the core of this lesson, as you hopefully grasped, was the idea of the structure of the atom. We have an atom, we have a nucleus, and it's surrounded by electrons, and then a whole bunch of definitions and terms related to that.